Hey everybody, Professor Davis here again for ChemSurvival Enterprises. And this time I'm going to talk to you a little bit about ring strain in hydrocarbons. So I'm going to start by reminding you small cyclic hydrocarbons, those of 3 or 4 atoms, are usually very unstable. They have a tendency to want to open up and become linear molecules instead of being those tiny little cycles that they are. And the question we're going to try to answer today is why that is. Now, 2 types of strain result when you have the closure of a small ring like this, and they add up to form what we call ring strain. The first of the 2 substrains is angle strain. Now, we know that a typical CH2 bond angle in a hydrocarbon that's, say, like, for example, a linear chain like hexanes, should be about 109.5 degrees. So we're going to take a look at a few small cyclic molecules and measure these bond angles to see how they match up. The other component is called torsional strain. And this results from the fact that an ideal staggered conformation of 60 degrees is not always obtainable in small cyclic molecules. So we'll be looking at them from a second perspective, which will allow us to assess those dihedral angles and determine whether they are contributing to this instability or whether they've reached an ideal dihedral angle. So let's get started. Let's begin by thinking about a simple linear alkane like butane, and let's just concentrate on the CH2 groups in the middle. We know that the angle among any carbons within that group should be about 109.5 degrees. And we also know that if we were to take a copy of this molecule and look down along the carbon-carbon bond in the middle, that we should see substituent dihedrals of 60 degrees, which corresponds to a completely staggered conformation. So in this case, when the molecule is free to twist, rotate, and flex any way it chooses, it can obtain these ideal angles, and therefore is expected to have no ring strain whatsoever. Shouldn't be surprising because it's not a ring, right? Now let's take a look at some of these small hydrocarbon rings and see what contributes to their instability. Okay, let's begin with cyclopropane. If we look at cyclopropane from above, the bond angles appear to be 60 degrees among the 3 carbons. And this is in fact exactly what the angles are, because if we tip this molecule on its side, we can clearly see that those 3 points are coplanar. Indeed, 3 points define a plane, so there's nothing this molecule can do to get these 3 atoms in any other angle than 60 degrees. Furthermore, if we sight along one of the carbon-carbon bonds in the ring, we can clearly see that the substituents, in this case hydrogens, have a dihedral angle of 0 degrees. So cyclopropane is locked in an eclipsed conformation. So let's put these numbers into the table. And if we take these values and we measure the cyclopropane stability, we discover that it's about 115 kilojoules per mole less stable than just a string of CH2s. Okay, now let's think about cyclobutane. Now, looking at cyclobutane from above, one might think that the carbon-carbon bonds are 90 degrees. Well, in fact, they measure to be about 88 degrees in cyclobutane. And that's because the carbon-carbon bonds twist a little bit to get these carbons out of the plane that would be defined by a flat square. But why then would this thing want to be 88 degrees instead of 90 degrees? Isn't that actually less stable? Right? That's farther away from the ideal bond angle. And you're right, it is. However, if we tip the molecule on its side, not only can we see this twist, but we can also see why this twisting occurs. The twisting places the substituents slightly out of this eclipsed conformation. So cyclobutane has angles of about 88 degrees for carbon-carbon bonds and about 22 degrees for the dihedrals of the substituents. So this relieves a little bit of strain, but not much. Cyclobutanes have a ring strain of about 110 kilojoules. So again, these molecules really want to open up and be long chains, not small rings. Okay, so let's move on to cyclopentane. Now, if we look at cyclopentane from above, if we were to assume that it is a flat pentagon, the bond angles should be about 108 degrees each. And that's very close to the ideal bond angle of 109.5. And yet, when we measure the bond angles within cyclopentane, we find that they're about 105 degrees, a little bit narrower. This is for the same reason that we find cyclobutane's carbon-carbon bonds to be smaller than expected. And that is that this molecule twists in a way that helps it to relieve some of the strain from the substituent dihedrals. Now, in the case of cyclopentane, not all of the substituent dihedrals will be identical. Because of the envelope conformation, these angles can vary from anywhere from 11 to 45 degrees. But the summation of all of the bond angles and all of the substituent dihedrals ultimately lead to a ring strain of about 26 kilojoules. So we've reached a point where the molecule is becoming large enough and flexible enough that it can achieve a conformation that relieves most of the strain. Finally, we arrive at cyclohexane. And if we look at cyclohexane just as we have all of our other molecules from directly above, it appears that the bond angles are too large. They're 120 degrees. But for the same reason that all the other molecules have had slightly smaller than expected bond angles, with the exception of cyclopropane, we see that cyclohexane has an ideal bond angle among its carbons of 109.5 degrees. This is because it's able to obtain a conformation we call the chair conformation. Notice that the 6 atoms are not all coplanar. And when the bond angles are at 109.5 degrees in this chair conformation, the dihedrals among the substituents are also a perfect 60 degrees. So at the point of cyclohexane, we've reached a ring which can actually achieve ideal bond angles and ideal substituent dihedrals. So placing these into our table, it becomes apparent that we've come full circle to the point where a cyclohexane ring has virtually no ring strain. So it should come as no surprise to you that you're going to see a lot of cyclohexane molecules as you progress through your organic chemistry course. Everything from very simple syntheses to larger biomolecules, we can find this kind of motif in them. And this is the reason why, because cyclohexane has virtually no ring strain. That's all for now. I'll see you next time.